So today we are going to continue talking about logistic regression models, and we'll basically generalize the binary logistic regression case we talked about last week and start talking about multinomial logit models. And so, like I said, a little bit of background, we'll generalize the 2-outcome case to 3 or more outcomes, and then we'll do so by doing a case study with some sample data. And so if you're able to log into virtual desktop, that would be helpful. You can basically follow along. But as we move forward, assignment 4, as you're likely aware, is the last homework assignment for the semester. And so over the last few weeks, we'll basically be introducing a number of additional analytical frameworks, different types of regression models. And so we'll be working with those through a series of in-class exercises. And so while we won't necessarily have any assignments with those data sets, you'll get some hands-on experience in working with those data. And in many of your cases for your respective course projects, you'll notice that some of these different methods we'll talk about may be pertinent to the types of data that you'll be analyzing. And so like I said, that next assignment is going to be due this Sunday. And then we'll also have some associated project check-ins that I'll circle back to later in today's slides. So before we get started on things here, does anybody have any questions in the audience? Okay, so hearing and seeing none. So oftentimes in transportation, we run into dependent variables that are discrete in nature, or not continuous. The outcomes of those variables or the different levels or categories can be classified into a series of distinct and discrete categories. And so there are a wide range of different scenarios in which we'd encounter this type of information in practice, looking at things like decisions as to what mode of travel an individual would choose during commuting purposes, for example, if they have auto, bus, transit options, decisions as to purchasing or leasing a vehicle of various types. On a daily basis, we have route choice decisions, at least during normal non-COVID times, trying to determine which route we take from a given origin to destination. And then we also have other types of data that are similarly nominal in nature. So if we look at the severity that results from a vehicle crash, well, there's an inherent ordering structure there. We can think about those as a series of discrete categories, and then we can develop discrete choice or discrete outcome models to help us distinguish what factors separate these decisions, or what factors would dictate the choice or an outcome that would result from these given choice situations. Okay, so basically we're trying to determine which of these different alternatives in these choice situations or these outcome situations is most likely to occur, and then which factors can help us to predict which of those outcomes may be more or less likely. Okay. And so this is all rooted in utility theory. So we can think about this as an economic problem as an example. And so if we think about the auto purchasing decision as an example, we can think about there are several different types of automobiles we'd be interested in purchasing. And each of those different candidates could be, define the utility of how valuable or how much utility an individual derives from choosing that automobile. Okay. And so we can basically think about the characteristics that we can measure that would relate to each of those automobiles. So things like the cost of the vehicle, its fuel efficiency, its acceleration, its emissions profile, whatever the case may be. There are a lot of different factors that may make that vehicle more or less attractive to different individuals. And so what we're trying to do from an analytical standpoint is basically specify a utility function that's linearly relating that utility to a series of measurable characteristics that we have or can collect data for. And then our problem essentially becomes estimating what these parameters, beta, in that beta vector, are going to be that would increase or decrease that respective utility function for each of the alternatives that we're comparing ultimately. And so if we think about a model of that form, as in any of the regression scenarios we've talked about up to this point, these relationships generally aren't deterministic. There's randomness and noise and stochasticity involved with these decisions. And so ultimately, we're going to add a disturbance or an error term to that function. And consequently, then, the way we're going to proceed when we estimate this model is we're interested in the probability of any individual or any observation n choosing or resulting in some discrete outcome of interest I. And we're going to compare that outcome to each of the other competing outcomes. And so in the case of purchasing an automobile, we would compare one make or model of automobile to the others that are available for an individual to purchase, as an example. And so generally speaking, a rule here is that those persons would tend to select the outcome that would maximize their own utility, is how we think about this in concept. Okay, so generally we're interested in the probability of the utility for any one outcome being greater than the utilities for each of the other competing outcomes here. So we're just denoting use of IN is the utility of alternative I for individual N, and then capital I here is basically the full set of other alternatives that are being considered by the individual in this context. Okay. And so if we substitute in this linear in parameters equation for UIN in that expression, we basically have what's illustrated here. And so through some algebra and just rearranging terms here, we can basically determine that the probability of an individual selecting alternative I or of an event resulting in outcome I can be thought about in terms of the differences in the probability or the differences in the values of these linear functions between those different choice sets. Okay, so ultimately we're looking at differences in the utility functions among those competing alternatives. Okay. And so when we think about that disturbance term, there's several reasons why we include that in our estimation and model formulation. Now, first of all, we've talked previously about omitted variables and how those can be problematic. And so consequently, we could observe the same or similar or the same individuals in different choice situations, and we might not necessarily see them make the same choice across all of those settings. And that may be due to the fact that we have important variables that for whatever reason are not being captured as a part of our analysis. We may not necessarily be capturing the functional form of that model correctly. And so as was shown in the preceding slide, we're assuming that those utility functions are basically linear functions in terms of the right-hand side variables. And so there may be some transformations that would be appropriate. Proxy variables. So if we think about that auto purchasing decision, we'll get to an example later today. We could classify each of those automobiles on things like whether it's foreign or domestic, or we might have luxury brands like Mercedes, for example, versus non-luxury brands. And I won't list any specifically there so as not to offend any of you in terms of the automobiles that you drive. But if we think about a variable like a luxury vehicle, that's serving as a proxy for some aspects of those higher end vehicles that we might not necessarily have data about, but we're capturing kind of qualitatively some of the differences that would inform that purchasing decision. And then lastly, if we think about the parameters in those models, it's likely that those may vary across alternatives. So price may be more or less important to some individuals. Likewise, when we talk about fuel economy or any of these other different scenarios. Okay, and so consequently, that error term helps us to accommodate the fact that not all individuals, or at least similar individuals based on the parameters we have in our model, are going to make the same decisions ultimately. Okay, and so we need to make an assumption as to the distribution of that error term. And so as an example, in the linear regression model, we assume a normally distributed error term with mean of 0 and variance sigma squared. In the discrete outcome case, there are two general assumptions that we would make. Either we assume that each of those utility functions, the error term would follow a normal distribution, and that results in what's referred to as the probit model, Or alternately, we can assume that those errors are going to follow a type 1 generalized extreme value distribution. This is also referred to as a Gumbel distribution in the research literature, and that would result in the multinomial logit model, okay? And so again, in the probit case, we're assuming those error terms are normally distributed, and so that cumulative normal function that you've seen before in different settings is as demonstrated here. So the probability of that particular alternative being selected, or y being equal to 1 in that case, is basically a function of the difference in the utility functions between alternative 1 and its competing alternatives. Okay, so this is just demonstrating for the 2 alternative case. And so if we think about the standard cumulative normal distribution, we can basically express that as indicated here. So the probability of an individual selecting outcome 1 is just basically the difference in the utility function between outcome 1 and some other outcome. And then that's just going to be scaled based upon the variance of those respective utility functions, okay, or the variance of those differences. Okay, so this is basically a standard error for that difference you see in the numerator of that probability mass function. Okay. And so we're going to estimate the probit model using maximum likelihood estimation generally. And so we're just going to define a variable delta, which is going to be equal to 1 if the individual selects that outcome and 0 otherwise. And so we won't go through long scale detailed derivation here, but just to give you a sense. So we've got a likelihood function basically. So the probability, we can calculate the probability of any individual selecting outcome I. And for each of those specific individuals, we can evaluate that probability, which comes from the expression you saw on the preceding slide. And if they actually selected that alternative, this variable would be equal to 1. If they didn't select that alternative, this delta variable here would be equal to 0. And so keep in mind, in maximum likelihood, we're taking each of the individual observations in our data set. We're calculating that probability, and then we're taking the product across all observations when we're trying to solve for those parameters beta. And so beta is going to basically be the vector of parameter estimates that would maximize this likelihood function. Okay. And so in the simplest case, the binary case, where we can just have the value of 1 or 2, that log likelihood function is basically shown as illustrated here. Okay. So you've got a bunch of values that are going to be raised to the power 1 or to the power 0. And so that's just being indicated here by those respective contributions to that log likelihood function. And so this is what is going to be maximized by the statistical analysis programs that we're using to derive the parameter estimates, the betas in this case. Okay. Okay, and so alternately in the logit case, if we assume those error terms follow the generalized extreme value type 1 distribution, you'll notice that's illustrated here. So it looks very similar in nature to the normal distribution. The big difference here is that we have a narrower and higher peak here, and consequently, we also see some differences in the tails of these distributions here. But generally speaking, the decision as to whether or not we look at a probit or a logit model isn't going to have much of a difference. There's been a lot of literature that's investigated this, and there's not really a strong preference for one versus the other. As we work through and estimate these models, we will see that there are some differences in terms of the parameter estimates, but by rescaling those, you'll generally get the same outcome regardless of what choice we make. So in practice, we typically work with a logit model when we go beyond the 2 outcome scenario, and the reason for that is because when we get to the multinomial probit model, when you get beyond 2 alternatives, we've got a multivariate normal distribution, and it's very difficult and time intensive to try to develop a solution to that. Whereas the logit model is a bit more friendly. It has a nice closed form solution because one aspect of the generalized extreme value distribution is that the maximums of values drawn from this distribution are also distributed as generalized extreme values. So we don't have that same problem we do in the multinomial probit case. Okay, so under this assumption, you'll see some familiar nomenclature here. So as in the probit case, we're basically calculating or maximizing here, determining the probability that any outcome of interest has a utility that's greater than all the competing outcomes. Okay. And so this should look somewhat familiar to you from last week when we talked about just the two outcome logistic regression case. So we can basically exponentiate the utility function for any given alternative, and we would just take that over the ratio of the sum of the exponentials of the utility functions for all of the other competing alternatives. Okay. And so at the end of the day, if we wanted to calculate the probability of an individual selecting outcome I, we could do so using this expression we see right here. Okay. And the corresponding log likelihood function is as shown here, with that delta being defined as it was previously. Okay, so that would be equal to 1 for whatever the choice scenario of interest is, and 0 for each of the alternatives that's not selected when we're going through and calculating the maximum likelihood estimates. Okay. And so one important note here, and we introduced this last week with the logistic regression. In the simplest two-case scenario, we can't actually estimate a utility function for models 1 and 2. If you think about the preceding functions, we were basically interested in what the differences in the utility functions were. And so consequently, in the 2 outcome case, and when we extrapolate this and go to 3 or 4 or more outcomes, we're always going to basically zero one of those outcomes out. So in the 2 scenario case, we would estimate one utility function and we would compare it to whatever the other category is. And so a positive coefficient would mean that that alternative is preferred, or as that variable increases, that alternative becomes more likely than whatever that case is that we've zeroed out or left as the baseline. Or alternately, in the case of a negative sign, that would mean an increase in that parameter makes that alternative less likely as compared to the baseline alternative that we've left out. This will become a bit clearer as we start working through an example here in a few minutes, okay? And as I had said, the logit versus probit choice is largely arbitrary in nature. So if we look at the distribution of the differences in the utility functions for alternative 1 versus 2 in the binary case, if those utility functions are equal to one another, of course, you'd expect there'd be a 50% chance you'd choose alternative 1 versus alternative 2, okay? And as alternative 1 becomes more attractive, or its utility function becomes larger than that of alternative 2, we'll see that the probability of selecting alternative 1 is going to get larger. And likewise, as that quantity gets smaller or negative or more negative and alternative 2 becomes more attractive, then our probability of selecting alternative 1 is going to get smaller, okay? Generally speaking, we see the similar type of S-curve for the logit or the probit model. And so from a practical standpoint, all this means in essence is that our betas are going to be scaled slightly differently, but at the end of the day, we're going to arrive at very comparable probabilities between those 2 choice scenarios, okay? And so the example we're going to work through today, we're going to return back to that State College, Pennsylvania travel data set where we had commuters making the morning commute from a residential area to a central business district. And so in that setting, there are a number of different routes that these individuals would have available to them. And so we talked about 3 routes in that example, but we can start with just the 2-route alternative. And so let's assume those individuals have the choice of taking either a rural highway or some alternate route that's available to them. And so what we do in this consequence then is we can specify utility function for the rural road and or for the other road. And what we're going to need to do here is zero out one of those. And so the utility function for route 2 in this case will set equal to 0. And so consequently, the exponential of 0, of course, is just giving us 1 back. Sorry, my dog is barking. Come on. Up. Okay, so we're going to have to, like I said, zero out the utility for one of those functions. So that just becomes exponential of 0 is equal to 1. And so the probability of someone selecting route 1 in this case would be the exponential of the utility function for route 1 divided by 1 plus that same quantity. Conversely, the probability of someone taking the other route would just be 1 divided by 1 plus the exponential of the utility for route 1. Okay? So this is identical to the simple logistic regression case we had introduced last week, okay? And the same concept here is basically going to extrapolate as we move beyond the two outcome case to 3 or more outcomes, okay? And so an important note here, we always need to set at least one of those alternatives equal to 0 because we're concerned in the differences of those utility functions. And so as we move to more than 2 cases, that brings us into the multinomial logit model, okay? And so we'll return again to that State College, Pennsylvania data set. And so you may recall we had 3 alternatives. So route 1 was a rural arterial, route 2 was just a rural 2-lane highway, and then route 3 was a freeway. And so we can think of this as basically estimating utility functions for each of those 3 alternatives. So the arterial has a series of measurable characteristics that describe it. And so we're interested in estimating what the effects of those variables are on the utility, likewise for the rural road and freeway. And so in each of these cases, we're assuming these error terms are going to follow that generalized extreme value type 1 distribution. And so consequently, the probability of someone selecting the arterial, which would be route 1 in this case, would be the probability of its utility being greater than the utilities for route 2 and 3 in this case, which again would be the rural 2-lane highway and the freeway respectively, okay? And so we'd have this general equation here to calculate the probability of an individual selecting route 1, the arterial road. Now back to the preceding point, we're going to need to basically zero one of these 3 alternatives out. And so consequently, as we look at this in concept, the way this works basically is, like I said, we're looking at the differences in utility. So it's arbitrary which of these we're going to zero out basically, but our probability of choosing the arterial in that case would be taking the difference in the utility between route 1 and then routes 2 and 3 respectively, okay? And so you'll see in each of these equations, when we're calculating the probability for this respective route, we're looking at the difference in the parameter estimates between that route and each of the competing routes that the individual has to choose from, okay? And so, as we said previously, we need to zero out at least one of these 3 cases here. And so consequently, just arbitrarily, we're zeroing out the freeway case. We're setting its utility equal to 0. And so then at the end of the day, our series of probability expressions are as demonstrated here, okay? And so with that information in hand, we can then go through and calculate the probability of someone selecting a given route for any given combination of the explanatory variables, okay? Now, when we're evaluating these regression models, we'd be provided with t-statistics, or some software will, instead of t-statistics, report out chi-squared statistics, which is basically just the square of the t-statistic, which is in a familiar form of what we've seen previously. So we're just getting our parameter estimate divided by its associated standard error. Last week, we had also introduced the likelihood ratio test statistic, or the LR test. And so as we had done previously, as you add variables to the model, that likelihood function is always going to improve. And so we're interested in assessing, we don't want to overfit the model, and we don't want to include variables that are irrelevant or not contributing to the predictive performance of that model. And so what we would basically do in this case is we would take the difference between the restricted model, which would include the fewer number of parameters. As we add parameters to that model, it's then unrestricted, so we're allowing greater flexibility then in that case. And that test statistic, if we take the difference in those log likelihoods and then we multiply that by -2, that's going to give us a test statistic that's going to be chi-squared distributed. And the degrees of freedom is simply going to be the difference in the number of parameters. So if we add 3 parameters to our model, that would be distributed as chi-squared with 3 degrees of freedom. Okay. And then we had also talked last week about the various types of R-squared analogies. And so in a simple case there, we had introduced McFadden's R-squared, which is also referred to in rho squared as rho squared in several platforms, which is just 1 minus the ratio of the log likelihood for the unrestricted minus the restricted model. Okay, so we talked about how a perfect fitting model, that log likelihood would tend towards 0, but in practice, we're never actually going to see that. But this is giving us a rough estimate that can be interpreted somewhat analogously to R-squared. But again, we're typically going to see lower ranges of that value as compared to linear regression models, okay? And so what I wanted to do for the remainder of today's lecture is just work through the sample data. And so this has all been provided in an Excel file on the D2L site. And so this is data from that same travel survey that was introduced previously. So these data were collected from a survey of 151 individuals outside of Penn State. They're all making the morning commute to work and going from the same residential area to the central business district. And so in doing that, they basically have 3 different roadways that they can consider. There's a 4-lane arterial, a 2-lane rural road, and then a limited access 4-lane freeway. We're given the number of lanes and the speed limits respectively. And so with that information in hand, we can estimate a multinomial logit model to determine how likely it is that any given individual would select one among those 3 competing routes, okay? And so that's the setup. The variables that we have to work with at this point are as shown here. So our dependent variable, variable 1 is just the route that's selected ultimately by the individual. So we've coded that as 1 for the arterial, 2 for the rural road, 3 for the freeway. We then have a number of characteristics that describe the driver and the vehicle, including whether or not they wear a seatbelt, whether they have passengers in the car, age, gender, marital status, number of children, and income. And then on the vehicle side, we have the model year of the car, whether it's domestic or foreign, and its fuel efficiency. And then we also have 3 pieces of information regarding those routes between the residential complex and the central business district. So we've got the flow rate in vehicles per hour on each of those routes. We have the number of traffic signals that are present along those routes. And then we also have the distance that the individuals would travel on those routes in tenths of a mile in this case, okay? And so we're going to work through that in a minute. Before we do that, I did want to bring up a quick note. And so instead of meeting on Wednesday, what I would prefer to do, just to make sure we're on track with our course projects, is schedule 15-minute check-in meetings. So basically just a brief update. And so my thanks to many of you. I think we've already got at least a half dozen of you had responded prior to today's class. And so basically between tomorrow and the end of the week, I want to just meet briefly, and I'd like you to prepare just a few simple summary slides. First of all, I want you to describe your data set. So summary statistics for both your dependent variable or variables of interest and any independent variables that we're interested in. And so those summary statistics would basically be the descriptive statistics we talked about at the start of the semester. So minimum, maximum values, mean, standard deviation, et cetera. Our proposed analysis approach. And so at this point, our toolbox really only includes linear regression, logistic regression, either in the binary or multinomial case. But we'll be introducing a few other families of models over the next few weeks as well. And so if we haven't got to that yet, I can at least give you a jump start on that. And then lastly, and most importantly, any questions you have regarding the project, data analysis methods, just general questions about either the data set or the science or the statistical method you're applying. And so if you could please complete that poll today, preferably either right now or right after class, and I'll actually copy that into the chat box in just a moment here, but that's also available on the announcements on D2L. And so that's what we have for content here. Basically, when we come back next week, we'll be talking about some count data models on Monday. So if your data are in the form of non-negative integers, so things we can count, like the number of crashes a person that are experienced at a given location, or the number of times a person commutes in or takes a specific route, or any choice that you can count the outcomes of. That's what we'll be talking about. And lastly, the assignment 4 is due this Sunday. And then, like I said, we're looking for preliminary results, hopefully a week thereafter. And so that would allow me a chance to give you some feedback so that you get a couple weeks to finish up and revise those analyses prior to the final project being due. Okay, so that is what I had in terms of presentation content for today. I guess if anyone has questions, I can take those now. Otherwise, I'm going to transition into SPSS real quick. Before I do that, I'm going to copy and paste that link for the poll into the chat box. Okay, and so that should work. I'll put it there a second time without the space at the end. Okay, so please fill that, and please try not to select the time that somebody else has selected, and I will try to get back to everybody by sometime this afternoon for those meetings, okay? All right, now with that, I am going to change to virtual desktop for my sharing, or remote desktop, sorry. Okay, and so you should all now see the data set for the State College Pennsylvania commuting data. Can anybody confirm that they're seeing that? Okay, and so like I said, the information provided here, our dependent variable of interest is the route that that individual is going to select ultimately, okay? And so when we're trying to run a multinomial logit model, there's a package under Analyze, Regression, Multinomial Logistic here. Okay, so I'm going to open that up, and a few points of interest here. So when we're estimating these models, the first thing that we need to do is select our dependent variable of interest. And so in this case, that okay, so timeout. It looks like you can't actually see the others' results in that poll. And so that is an unexpected consequence. I guess I should have used Doodle, but I digress. So fill out any times that work for you, and then I'll just download that matrix, and I should be able to work around things on my end. So if you can provide your schedule, I'll just overlay that with my schedule. We should be good to go. Thanks for the heads up on that. Okay. Now back to the analysis. So like I said, in this case, the route is our dependent variable of interest. And you'll notice we talked about this last week in terms of how some of the packages, it's arbitrary which reference category is zeroed out. And so in this case, we've got 3 routes. And you'll notice by default, it's going to select either the first or last category as the reference here. I believe by default, it chooses the first category. And it's also going to ask whether those data are in an ascending or descending order. Those are basically arbitrary decisions, particularly in this case where there's not a natural ordering between the arterial, the rural road, and the freeway necessarily. And so I'm just going to leave them as first category, ascending order. And the first thing I'm going to do is just run this simple model here that's going to include only constant terms, okay? And so in doing that, I've noted previously, we've left out our reference category. and set that equal to 1. And so what we see here are basically outputs for the intercept term for utility functions for route 2 and route 3, okay? And so with this information in hand, what we can do, okay, now hold on for 1 second. I know this got a little bit messy last time when I tried it, but I'm going to use the whiteboard here real quick just to demonstrate what those results we just saw mean, okay? And so we had the utility function for alternative 1, we have arbitrarily set equal to 0. Okay, so we've zeroed that out. That serves as our reference case. In this simple model that includes only constant terms, we find that the utility function for the second route is going to be 1.138, which again is just the constant term. And the utility function for the third route is going to be negative 0.788, okay? And so with that information in hand, we can basically determine what the probability is in the simple model of people selecting any of those 3 routes, irrespective of what any of the other values of the parameters of interest would be, okay? So the probability of an individual selecting route 1 is simply going to be equal to 1 divided by 1 plus, let's see here, 1 plus the exponential of 1.138 plus the exponential of negative 0.788. And that is going to be, hold on, I'm going to quickly calculate that for us in Excel. So exponential of 1.138 and the exponential of negative 0.788. Okay, and so the probability of an individual selecting route 1 would be 0.2185, 2186. Likewise, we could determine the probability of an individual selecting route 2. That's just going to be the exponential of 1.138 divided by that same denominator. So 1 plus the exponential of 1.138 plus the exponential of negative 0.788. And we're going to find that that is going to be equal to 0.682. And then thirdly, the probability of someone selecting the freeway is going to be the exponential of negative 0.788 divided by that same denominator, 1 plus the exponential of the utility function for the rural road plus the exponential of the utility function for the freeway. And we could determine that either by taking 1 minus those 2 values or by explicitly evaluating that same expression. And either way, we'd get a probability of 0.099 in this case. Okay, so roughly a 10% chance of selecting that route. Okay, and so I'm going to quickly stop that share and then reshare remote desktop. And so as you look at those results, in this case, this is just telling us the basic underlying likelihood of individuals choosing one of those routes versus the other. And you'll notice the probabilities we just calculated are exactly in line with those actual distributions within our sample data, okay? So the probability of an individual taking route 1 is 21.9%, 68.2% for route 2, and 9.9% for route 3 as demonstrated previously, okay? Now, in concept, it is conceivable that we could have scenarios where we estimate the model and each of these betas is equal to 0. Can anybody tell me what that would mean in practical terms if those constant terms were all equal to 0? Okay, so if each of those utility functions is equal to 0, all the constant terms are equal to 0, what would that mean about the share of individuals who are taking each of the routes? So again, it's not reflected by this data per se, but if each of these intercept terms was equal to 0, what would that mean?
I mean, nobody takes that route.
Say that again, Falarin?
There's nobody takes that route.
Well, careful though. So what I'm saying in the same setup we had previously, so we've zeroed out the utility function for route 1, right? And we've estimated the utility functions for routes 2 and 3 is what I'm saying here, but those parameter estimates are now equal to 0 instead of this. So if all of our utility functions are equal to 0, what would the probability of us taking any of those routes be? Anybody? I may have worded
33%.
Yeah, exactly. I might have set that up somewhat ambiguously, but 33%, right? If all the utility functions are equal, we exponentiate that. So e to the 0 for each of these would just be 1/3 of the probability of an individual taking any of those 3 routes, right? And so I just wanted to bring that up because that's just reflecting the constant term is basically giving us the baseline distribution of our data here. And what'll happen as we add predictor variables to our model, we'll find that these coefficients, these constant terms are going to change as a consequence of that because now we're collecting additional information. But I just wanted to illustrate, once we've conditioned for the effects of those other terms, the constant terms are just telling us then what the underlying baseline probabilities are if all those variables are equal to 0, okay? And so we'll get back in and demonstrate this. So let's just say we add, what would be an interesting variable? Probably the distance that individuals are traveling on those routes. And so in this case, I'm going to add the variable for the distance individuals are traveling on the arterial route, okay? And I'm going to add that as a covariate. I don't recall if I talked about this last week or not, but we have covariates and factors. If we enter the variable as a covariate, it's basically going to treat that as a continuous variable. If we entered it as a factor, it's going to assume that variable is discrete in nature, and so it'll estimate a series of binary indicator variables. So we definitely don't want to do this for arterial distance, and I guess I can demonstrate in a second what happens if we try to do that. But so all I'm doing right here, I'm including this arterial distance model in each of those 2 utility functions for routes 2 and 3 essentially here, okay? And so I'm going to hit OK. Okay, and so now we see the output results right here, okay? You'll notice there are marked differences in the intercept terms here. We also see some impacts of the arterial distance. And now to refresh everybody's memory, the arterial was route 1, the rural road was route 2, and the freeway was route 3. So as we think about this, what are these results telling us generally speaking? So we see arterial distance in the rural road equation is equal to 0.171, and in the freeway case is equal to 0.781. So just from a qualitative perspective, empirically, what are those data suggesting to us? So as the distance a person would have to travel on the arterial road increases, what's happening to the utility functions? So just thinking about this conceptually, as the distance you have to travel on the arterial increases, is that arterial going to become more or less attractive to us?
Less attractive.
Yeah, it's going to be less attractive. Okay, now in this case, interestingly, I selected that, and we've zeroed out that function. but we can think about that in concept. So if the arterial is becoming less attractive to us, that means that the other two routes are becoming more attractive, right? And so to that end, we see that the coefficients are positive in each of these other cases. And so it looks like as a distance along the arterial increases, people are tending to shift to the other routes, and they're shifting more strongly towards the freeway route in this case, it appears. Okay. Now, we can continue to add some variables, and it'll become a little bit more clear if we add the distances along each of those respective routes. Okay. And so I'm going to rerun the analysis here. And so now what we're finding, keep in mind, this is the rural route, this is the freeway, we've zeroed out the arterial. And so as you'll see here, as that distance someone has to travel along the rural route increases, it's becoming much less likely that someone would then choose the rural route as its distance increases. And the same is true on the freeway. So as the distance someone has to travel on the freeway increases, the utility function for that freeway is decreasing significantly as well, and it's becoming less attractive to us. Okay. And then we can see what basically, so that's the direct effect of the distance for that specific route on its likelihood of being chosen. But there are also some indirect effects that are being captured in the other variables here as well. So generally speaking, the distance parameter is tending to be negative for that specific route that it's in reference to. But it's also tending to then be positive and making the other outcomes more likely for the competing routes. Okay. And so when we're looking at this, what we'll tend to see generally is that there'll be more significant relationships when we're looking at the direct effect. So anything that's specific to the rural route is going to tend to have a stronger influence or be more significant for that rural route. Likewise, generally in the freeway case here, so that freeway variable, interestingly, it's not statistically significant. And a part of the reason for that is that we only had 9.9% of our sample actually selected the freeway. And so generally speaking here, we don't see a lot of highly significant variables, but this is how we work through this in concept. Okay. Now, the other thing I wanted to demonstrate here, keep in mind, we're interested in the differences in these utility functions across routes. And so it's arbitrary which we set as the baseline category that's been zeroed out, okay? And so I'm going to run the exact same analysis here, except I'm going to zero out the freeway instead of the arterial. And so as we had seen before, as the distance on the rural road increases, it becomes less desirable to us. As the distance in the arterial increases, it becomes less desirable to us. Interestingly, we do also see that as the distance on the rural road increases, the likelihood of taking the arterial actually decreases as well. And so it looks like collectively what's probably happening here in this residential area, if you're very far away from the central business district, it looks like there's a general preference towards the freeway versus either of those other routes specifically. Okay. But what you'll notice here when we look at these model parameters is that these are they'll be consistent across the different categories here. So if you look at the freeway distance, in the prior case where we had zeroed out Route 1, that effect for freeway was 0.312 larger. So that parameter is positive 0.312 when comparing Route 2 to Route 1. Okay. And then when we come down here, what we're going to see is that we'll ultimately have those same general differences across the categories. Okay, so here we again see that 0.312 difference between the freeway distance in categories 1 and 2. So the relative scaling of the variables is going to be identical regardless of which we've zeroed out as our base case. Okay. And so that decision is basically completely arbitrary in nature, okay? And so we'll find when we look at the goodness of fit statistics, so these are those, pseudo R-squareds we had talked about previously. You see our log likelihood statistics here as well. And so this is just giving us a general sense of the predictive power of these different distinguishing factors, okay? And so a few other items I wanted to demonstrate quickly as we work through the multinomial logit model. We can also look at the effects, and so to keep the output simple here, let's say we want to see whether there's any relationship between income and the route that's selected. Okay, so as you may recall, income was classified into 5 discrete categories, and so those are increasing in magnitude. And so if we hit OK here, we may see some general patterns in the data here. So it looks like, well, first of all, it looks like we've got a problem here with income, and so we're comparing that income variable across the categories here, and we're not seeing a very strong effect, generally speaking. And so it looks like there's a weaker effect, so p-value of 0.25, whereas income increases, people are less likely, at least slightly less likely to take the rural route as compared to the other routes in this case, okay? Now, if we were to let's look at maybe a different variable that has slightly fewer categories. Because one thing that's happening here with income, keep in mind our sample sizes are relatively small here. We've only got 151 individuals, and only 15 of those 151 are taking the freeway. And so let's take something that's a bit simpler here. Let's just do single versus married. And so in this case, it looks like for whatever reason, there is a slight preference for those single individuals to take the arterial. And then likewise, there's also a slight preference for those individuals to take the rural route, and they're less likely to take the freeway. And we really don't have any idea what the reasons for that decision are necessarily here. But looking at those individual parameter estimates, that effect isn't statistically significant in either of these cases. And what we see up here, these likelihood ratio tests, so this is basically simultaneously testing whether there's a general effect in including that variable in each of those utility functions, okay? So that single variable is included in 2 of the different, it's added as a variable in 2 of the utility functions, so there are 2 degrees of freedom associated with it. The actual improvement of goodness of fit in the model is very small here in this case, though, and so that p-value is nowhere near significant, okay? In contrast, the intercept term here does show a strong effect, and just as we had talked about in the linear regression case, even if that intercept is not significant, you would definitely want to still include it in your model here, because if you don't include that, we're going to likely see some biased effects due to the correlation within the variables in our data set, okay? And so this has basically provided you with enough information to estimate the models and be somewhat dangerous in doing so. I guess at this point, does anybody have any questions as to the estimation of the multinomial logit models, or interpretation of the parameters, or just any general questions on the model building point?
Can you go over the estimation of the parameters like one more time, if you can? Just some of them.
The interpretation of the parameters?
Yes.
Sure. Okay, so I'm going to try the same strategy where I use the whiteboard here, so bear with me. Okay. Okay, does anybody know how I clear it? Perfect. Okay, so in this case, what we've done, just as we had seen previously, if we enter the utility function, at least for the last model that I had run, the utility function for route 1 is equal to 0.619 plus 0.297 times that variable, whether or not that individual is single, okay? For route 2, its utility function is 1.838 plus 0.160 times that same indicator variable as to whether or not that person is single. And U3 is the alternative that we've zeroed out in this case, okay? And so as we look at these results, there are a few points of interest. And one for whatever reason, I didn't even have a slide on this. So I'll revise the slide deck here. As in the case of the binary regression, we can also calculate the odds ratios. So we can interpret, as you recall from last week, the odds is just the probability of an individual in this context selecting route 1 divided by the probability of them selecting any other route, okay? And so if we want to understand what the impacts of these parameters are, we can basically exponentiate the beta coefficients here, okay? And so as an example here, the odds ratio for marital status, we find for route 1 EXP 0.297, and that gives us 1.346. And so what that means is that, and keep in mind this is for marital status single. So what that means is that single individuals are 34.6% more likely to take the arterial road than those persons who are married, okay? Likewise, if we look at the rural road, exponential 0.160, that is 1.173. And so similarly, single individuals are 17.3% more likely to take the rural road than are married individuals, okay? And so that's essentially how we're looking to interpret these parameters. We could also, let's say for whatever reason, we're interested in specific ranges of variables. We want to know how sensitive some of these different parameters are. So if we go back to the example where we had the distance variables, in that case, we could determine for a 1 mile increase in distance or for a 1/10 of a mile increase in distance, whatever the case may be, what the corresponding difference or result is in terms of the change in probability of an individual selecting one of those routes versus the others. Okay, does that make sense, Valoran? Okay. Other questions from any of you? Okay, so at this point, we've got about 20 minutes left. And so I would encourage you all to just work around and try to estimate some multinomial logit models here, try to see if you can find any meaningful relationships between these respective variables. There are a few items we could potentially investigate here that weren't actually captured in the data set. And so one example I wanted to share there, we were given what the speed limits on these respective routes are. And so while that's not included as a variable here, we could have included that. There are various other ways we could look at this as well, but ultimately, there are some insights we can get from this data set. The one big limitation is we only have 151 individuals who we've observed in this case, and so it's going to be challenging to find relationships that are statistically significant, just given those limitations in the sample. But nonetheless, this does give you a fairly good introduction to the estimation of these models, because there are a few different variables that are either unique to the specific route or unique to the individual, but would be the same across each of those choice settings ultimately, okay? And let's see if there's anything. I guess there were a few other items I had talked about, but maybe not circled back to. So one of those if we take the variable, well, single, I guess, is in, there's only the two groups there, but let's look at a variable that has more than two outcomes. So let's say the number of traffic signals that are on the rural route. We can include that as a covariate in our model. And so as you see here, the more signals there are on that route, the less desirable it is. And so we basically treated that as a continuous variable. We could also treat that as a factor rather than a covariate. And so as I had alluded to previously, what that does is it estimates a series of binary indicator variables instead of treating that variable as continuous. Now, in this case, the one thing I should note, and the one thing you should potentially be concerned about when you're estimating these regression models, is this warning we see up here where it says there are unexpected singularities in the Hessian matrix. And so what that basically means is we're overestimating our model or overfitting our model. And so when you scroll down to the results here, this is basically showing us, so rather than treating signals as a continuous variable, it's just basically estimating a series of binaries. So it looks like there were 6 different, among the 151 individuals in that sample, they were located such that there were 6 different scenarios they could run into in terms of the number of signals along that rural route. So those range from 3, 7, 8, 10, 11, and 13. And so what you're seeing here, there are a lot of very, very large, in this case, negative numbers, which means we probably have very small subsets of individuals in those respective categories, which is true if we go up here, okay? So there was only one individual who had a choice path that had only 3 signals. There were only 2 individuals that encountered 11 signals, and there were only 5 individuals that encountered 13 signals in that setting, okay? So it probably doesn't make sense to include this as a series of indicator variables, and so I just wanted to reinforce that point here. The same thing would happen with income or any of those other variables that have large numbers of categories. And so that's just something to be mindful of as you're building these respective models. So generally speaking, we want to make sure that there's sufficient coverage. And anytime you see parameter estimates or particularly standard errors that are very, very, very large in magnitude, at least in terms of their absolute values, that means that there's a problem. There's probably a separation in our data. Okay, so what that means, to include these variables in the model, you'd want at least some degree of coverage. So you won't want the individual to always choose the same route for certain values here, because you wouldn't be able to capture that effect if the data are completely separated in that nature, as appears to be the case for, again, the case where there are 3 signals or 11 signals, which were our 2 smallest samples as shown above, okay? And then, like I said, in other variables like distance, we'd already shown these outputs. If you treat distance as a continuous variable, which probably makes the most sense, we see results that are clean and seem to be consistent and not show any problems. We could also include that variable as a factor. I would very strongly caution you against doing that. So just to show you what happens when we do that, it takes, so these are each of the different distances that individuals are traveling over that route. And so it's trying to estimate a series of indicator variables for each of those individual distances, okay? And so obviously our sample size isn't large enough that we could estimate that number of parameters reliably. And so the whole model basically blows up at this point, okay? But just something to be mindful of, because occasionally when I'm reviewing manuscripts, I have seen cases where people will submit results from models that are over-identified, and that's very clear from the model outputs here. So, okay, and then the one other point I guess I should bring up when we talk about the odds ratios. So I'll just show us here for those distance variables again. So in addition to giving us, like I said, beta, our standard error, if we wanted to treat this as a t-statistic, it would just be beta divided by its corresponding standard error. That walled statistic is just basically beta over standard error, that whole quantity squared, okay? And so 1 divided by 0.8, that quantity squared gives us 1.597. in each case, we get the p-values, and it also gives us direct output as to the odds ratios here. And so again, when we're interpreting these, what this means is that for a 1 unit distance increase, or for a 1 unit increase in distance along the freeway, the arterial sees a 175% increase in the odds of someone choosing the freeway, or choosing the rural route in that case. And in the other cases, as these distances increase, since these odds ratios are less than 1 because these parameter estimates are negative, it means that there are decreases in the probabilities of individuals selecting those respective routes, okay? So that's basically given directly as output here. Interestingly, it also constructs 95% confidence intervals here. And so in this case, what you'll notice, so these are confidence intervals around the odds ratios, around that exponential of beta. So in this case, we want to check whether or not these intervals include the number 1.0. Okay. So in this case, this odds ratio ranges from 0.198 to 0.921. And so it doesn't include 1, which means there's a significant difference there. And that's reinforced by the fact that this p-value is less than 0.05. Okay. Whereas in the case of these other variables that aren't found to be statistically significant, those intervals do include 1. So those odds ratios are not significantly different from 1. If the odds ratio is not significantly different from 1, that also means that the parameter estimate is not significantly different from 0. Okay. Okay, so a whole lot of information there. Let's see. We've got any questions? So I see one in the chat box. So if we do observe data separation, would removing outliers solve the problem, or does it root from a different cause? Yeah, so when we talk about data separation, the only thing we can really do in that case is just not include that variable in our model, because what that means, and I guess in the most extreme case, if we scroll back up to the prior examples here, so rural signals, there's literally only one person who had, 3 signals encountered along the rural route. And so that sample is just not sufficiently large enough. We need to actually see observations generally within each of the 3 categories, okay? And so our sample size is simply much too small to look at many of the variables in this case. And so I guess the short answer is, to rectify that, you'd have to go out and collect more data, practically speaking, if we wanted to figure out what that actual relationship is. But if you run into this issue as you're conducting the analysis, you're kind of stuck. Now, one alternative, if we go back to the number of signals example, is, well, you could just treat it as a continuous variable. And so that becomes less of an issue. Though even with continuous variables, we can see separations, but it's generally more of a concern when you're dealing with indicator variables. And so if you do run into that with indicator variables, one thing we could do is group similar values together. So in case of the number of signals, we could take, say, 0 to 10 and group that in, and then 10 to 15, or whatever the case may be. We could try to aggregate those so that we at least have sufficient coverage there, okay? And so hopefully that gives a little bit more insight. Any other questions from anybody? Okay, so if not, I guess with that, please fill out the when is good poll again. I will actually, let me click on it real quick. If I got responses from everybody, then I can get these schedules hopefully right before. Okay, so I see 12 responses so far. So it looks like I'm waiting for one person to provide their availability. And so once that's done, I'll send out calendar invites later today, and we'll try to get these set up as soon as humanly possible, okay? Okay, any other questions before we wrap up? Okay, one more question just came in, so let me briefly address this. Is there any explanation for the intercepts for route 1 and route 2 once we have included the parameter estimates? Great question. Let me reshare my remote desktop. And apologies, today's recording is going to be a little bit rambling, and I don't really have a clean way to edit that, so we'll just have to make do. So if we go back and we look at, okay, so in this case, the intercept terms, they still give us meaningful information. So there are two ways to think about this. So one way to think about it is if all of these variables, all of our x's are simultaneously equal to 0, that gives us an estimate of what the relative shares are of those variable of that route choice decision. Now in this case, that's a nonsensical number because your distances would never be 0, obviously. But the other way we interpret this, and back to the preceding point from the lecture slides, these intercept terms are basically capturing the effects of everything else that's not included or captured in the model, okay? And so with that being said, if persons are traveling the same distances, this is telling us how much more or less attractive these different facilities are after having conditioned on that distance, okay? So the intercept basically tells us once we've accounted for all of the other factors, this is how relatively attractive these are after accounting for those other parameters. Now back to the initial question that I was asked here. I guess hypothetically, it could arise the circumstance where our model is so well specified and we've got such good data, or there's such a clean relationship here that these intercept terms would revert back. They'd be very close to 0. I'd still recommend keeping those in the model, but if those are close to 0, that means that the vast majority of your explanatory power is being captured by these variables, okay? And so to that end, the intercept term is basically telling us, giving us a sense of how much preference there is for one of the routes here in consideration of all other factors besides distance, essentially. Does that make sense? Okay. All right. Any other last minute questions?